Fellow speaker belong important company, young company in Romania, big step, and Alex Bordei will speak about memory, big data, NoSQL, and virtualization. Nicio problemă.
Doi, mă auziți, se pare? Complet, fără nicio legătură cu tocul meu, am văzut chestia asta azi dimineață și mi se pare foarte interesant. Nu știu dacă știți de ea. E un proiect crowdsourced în care unii s-au gândit să aplice ideea lui Carl Sagan de a trimite un fel de navă în spațiu care poate fi împinsă de către razele solare, pentru că se pare că fotonii au, deși n-au masă, au impuls. And then I'm going to switch back to English for all the other guys. I was saying that this is a very interesting project that is mimicking what Carl Sagan did about, I think, 20 years ago, when they had to move. He imagined this big sail that was pushed through space by the momentum of photons, and this guy actually they built this crowdsourced project when they pushed this into space actually a few weeks ago. And so it looks like this, but it's very, very small. It's actually like this. It's still just a prototype in space. But anyway, I found it very, very interesting. Let's see if this thing works. All right, so this is going to be a very technical talk. And it's going to be about memory in general and in-memory applications. But before we get into who I am and what we do and, you know, a lot more details, I would like to hear a few things about you guys. How many of you are, you know, can call yourselves developers? Absolutely great. All right, so how many of you have actually installed something like Hadoop by themselves? So that's about 40%. How many of you know what a huge page is? Or actually page table? All right. How many of okay, who knows what the transparent huge pages settings is? All right. Who knows what the TLB cache is? Wow, it's I mean, usually people end up at the last question as a single guy somewhere. Now we had about 4, which is, you know, it's raising the bar a lot for me. So again, I'm a developer, and I've been turned product manager for the last few years. It wasn't necessarily my idea, but apparently I end up building products for Big Step, and I won't talk about Big Step unless, you know, you really want me to, also a little bit at the end. And the plan for today is to talk about all the things that I've been asking you about and how they influence memory, and you'll get a feeling of why I'm talking about this in a second. And the idea is that recently you've been hearing, especially in the big data space, but not necessarily, you've been hearing a lot about in-memory processing, right? So there are a gazillion in-memory technologies popping up here and there. I could just name a few things like Spark, things like, you know, more recently, I think somebody from the audience told me about Druid.io. So there's a lot of new technologies that essentially they're moving into this paradigm of hosting, you know, essentially holding the entire data set in memory and just serializing it on disk. And this has become possible because of this, essentially because memory is getting a lot cheaper than it used to be. And what I did here is I tried to give you an idea of the differences in performance between different memory tiers. I kind of scaled them to human time. So one CPU cycle, if one CPU cycle would be 1 second, then accessing a memory DIMM in my CPU is about 3 minutes. Accessing a cache, the L1 cache is about 3 seconds. Hitting an SSD is about 4 days. Hitting a disk is about a year. So it's, you know, it's a hugely different. You don't have to remember this. I'll get back to them later on. So storage hierarchies used to look like this. Essentially, what's not on the disk is fast. What's, you know, so it was really simple. Now, if you think about getting the disk and the SSDs out of the equation, you start to see a few things that you haven't been paying attention to up to this point. And it is important to know about these things because they can greatly affect the system designs that you guys are building. Because, for instance, accessing memory locally to a particular CPU socket is a lot faster than accessing memory on the other CPU socket. And also, if you hit a lot of TLB misses, you get a lot of performance penalties. Again, I'm gonna get back to these things. So, the CPU architecture, the things that you learn from school, and you know, your mental picture of what the CPU and memory looks like is like this, right? So there's a CPU, some cache, and then the memory, which is a contiguous block. But actually nowadays, things look like this. You have multiple sockets, you have multiple cores on the same socket, you have a connection between the CPUs, which is called a QPI link, which influences a lot of things. So this difference in complexity, this is because of me? Okay. So the difference in complexity, it has various implications in terms of performance. Essentially, you have to design different algorithms to work around the differences. For instance, algorithms need to be parallel by design. So you can't just take something that has been built, 10 years ago and say, hey, I'm going to scale this up to on this new architecture, because it will simply not work, because a lot of our predecessors made decisions of sacrificing efficiency in terms of time for memory efficiency. But now these sacrifices don't have to be made. So completely different architectures now can be used, and this is what drives this innovation. Now, again, getting back to the cache hierarchies, what I want you to remember from this is the QPI link, this thing here. So whenever you consider buying some hardware, let's just assume for a second that you own some hardware for your company and you have to play with it and you have servers. If you have a choice between a dual socket machine and a single socket machine, you have to think about the fact that actually dual socket machine might be slower than a single socket machine on the same machine because of this QPI link. And I'm going to show you some benchmarks that says that. It's because if you're, and by the way, the operating system doesn't know how to actually allocate properly memory. So if you have memory that has to be accessed by this core here, that is actually residing in the DRAM here, what happens is that you have to traverse the QPI link, so you get a performance penalty. And operating systems are very bad right now at optimizing this. There are solutions and I'm going to tell you later. Again, a very interesting thing, every CPU socket has PCIe controllers. This means that the network card here will have difficulties. If you have an application on C1 there that's pushing data to the network card here, it will have to traverse the QPI link again. So all these latencies add up, and knowing about them will make you double or triple or increase tenfold performance improvement from our applications just by pinning a process to the proper NUMA node. So keeping memory and computation within the same NUMA node. And to give you an example of the differences, this is a benchmark that we did a while ago, and it was a benchmark done with Impala, by the way. And we've taken Impala and it's a lot more complex benchmark. But the idea is that in this particular scenario, we had a single CPU machine, dual CPU machine with the same CPU in two configurations, and in both situations you got less performance from a dual CPU machine, which is odd, right? You would say, hey, I'm buying more processing power, it's gonna be a lot better, but it's not like this, unfortunately. So a little bit of an intro of what actually happens when you try to access a memory cell from your application. By the way, how many of you have programmed in C, or actually programmed in C? All right, perfect. So whenever you have a pointer, right, you've been playing with pointers, pointer arithmetics, you're not actually hitting the real memory directly. You have what's called a virtual memory, because every application has a virtual memory block, like a continuous block of memory which is allocated to it, but it's not the actual physical memory address. This is because for security reasons and for performance reasons. It's a mechanism that was invented in the 70s to allow over-provisioning and over-allocation of memory. So if your application needed, twice the amount of physical memory available, you could spill over to disk, and you had what's called a swap that we all disable right now. And this mechanism of virtual memory addressing and physical memory addressing requires reverse mechanism of figuring out what's the actual physical address in a memory DIMM whenever you have to access it, right? And this mechanism is, it's called the page table translation, because operating system does not allocate for every single virtual memory address real address. It allocates it in pages, right? And the default page size is about 4K. So whenever you're allocating, you're starting up an application, say, hey, I want a page of memory. That's going to be a 4K page of memory, and the operating system maintains that page table. I know this is fairly complicated, but hear me out. Now this translation is done. If you would have had to do it manually, you would have to access memory twice for every memory access, because first you wanted to find out where your actual data is in the memory DIMM, and then get the data from that actual DIMM. So in order to avoid this dual accessing, there's a little fourth cache in every CPU, besides the L1, the L2, and the L3 caches that you know about. And I assume it looks like this. The L3 is shared by all the cores. Now, besides those that you know of, there's another fourth one which is a lot less known, which is the TLB cache, which is very, very small. It has 4K, and it does this translation. It helps the CPU do the translation and access memory a lot faster. So this is the first stage of accessing a particular memory segment. And then the second one is trying to figure out if one of my cache levels actually have seen this memory address before, and whether they actually store the data in there. So it's very important to try to optimize the miss ratio of the TLB cache, because there are performance implications, and I'm going to show you exactly what. And also about, of course, trying to optimize the cache entry. So a TLB miss occurs, again, when the memory address that you're trying to access is not, it's not known by the TLB cache. And when that happens, you have to traverse the entire page file to identify where your memory address is, which is a file residing in the operating system, actually. And the problem is that page file, if you have a server with 128 gigs of RAM, try dividing 128 gigs by 4K. So you'll get page file sizes of gigs, right? And traversing something which is a gigabyte or a few gigabytes or 5 gigabytes is very, very, very slow. So, and this actually happens on bare metal machines. It happens everywhere. It's a legacy. Yeah, go ahead. The TLB what? The TLB miss. This is a study done by the guys at Intel. They try to identify the characteristics of various big data applications, and they did very. Actually, there are tools. So there's a little C application that first starts with a very small memory segment that they try to access, and then try to increase the size of the memory that you're accessing. until you start getting a lot less performance. So this is how they do it, and they do it repeatedly, and it gets slower and slower because and the randomness of it will incur TLB misses. But there's this entire study that describes how this is done, and you might want to look this up. They did the study on not only the TLB miss, but also the L1, L2, and L3 cache efficiency, and what they and they did it for big data technologies. They oddly enough they didn't say anything about which NoSQL technology, but apparently the highest TLB miss happens about once every 1,000 or 2,000 instructions. So it's very, very, very seldom because you have a lot of instructions. So it's microseconds. And the problem is that essentially the CPU waits a lot for these things to happen. Okay. That's usually a TLB miss is about twice the DRAM latency, and as I said, it's about once every for big data technologies, it's about once every 1,000 instructions. Let's say like it's in that ballpark. And for big data technologies and for NoSQL, that happens because of the pattern of accessing memory, right? So whenever you have like something like Couchbase, and you have a lot of random accesses in different locations in the entire memory space, then the cache efficiency of the TLB is a lot less, right? So it has to do with the memory access patterns. But and on bare metal, it takes about twice the DRAM latency. But the problem is, so it's a very, very big problem that people are not aware, is the TLB miss penalty on virtual machines. And this is so because a virtual machine has a virtual, memory. So it's essentially you're doing a three-way translation from virtual to physical translation, because a virtual machine has a page file itself, has an allocated memory. So this translation is very, very slow because it's not, the initial implementations of virtual machine mechanism like QEMU were tremendously slow. I don't know if you played with QEMU before, but now to make this a lot more efficient, people from VMware initially, they've implemented something which is called a shadow page table to help translate directly from the virtual space of an application inside of VM to the physical space, to the physical DRAM, not going through the hypervisor. But the problem with that is that whenever a virtual machine will enter the context of the CPU, you would have to flush the TLB cache altogether, because the new virtual machine, the TLB cache for the new virtual machine will make no sense for the other virtual machine. So that's why you had to do these translations. And nowadays, what they did was, Intel came up with the idea, well, let's try to make it a little bit more intelligent, this mechanism. And they took the TLB, they added an extra information in there, which is called, I remember, I forgot how it's called, but the idea is that it's an identifier that identifies the process in a VM uniquely across all VMs, so that you don't have to flush the entire TLB cache whenever you're doing a VM exit. And please. I'm gonna get to containers later on. Okay, so and so by doing so, they've increased the complexity of the TLB. And as a byproduct of this, what they did, unfortunately, they increased the TLB miss ratio penalty because of the complexity of the entire TLB. So whenever you had the TLB miss, now you had a lot more stuff to do to try to identify where your memory address is. And this is something that it's a lot less known, but essentially what this tells us is that running big data applications in virtualized environments is not a great idea. You're going to automatically lose a lot of performance from it. So to give you an idea of what that means, this is another study that we did, and you can all, do it at home. There's a tool called a sysbench, and you can use it to read and write a terabyte of memory to and from the memory, right? And try to do it on a virtual machine, and try to do it on a bare metal machine, and this is how the performance will, differences will look like. Again, this is not I mean, not all hypervisors have this performance level. This is essentially state-of-the-art hypervisor that we use. So usually you get less than that. But, you know, your numbers may vary, your mileage may vary. Yeah, please.
Okay, so my question is related to the benchmarks that you. So usually when you are developing a big data application, the biggest penalty you have is during the shuffling of the data between the nodes in a cluster. When you are doing groups, reduces, and that's where is the place where you are losing. In your benchmark there it shows like, okay, it's pretty clear that when you're going to read and write 1 terabyte of memory on a single machine, of course it will work faster because it's one single machine. But
no, I agree.
What's the performance gain in a cluster? I'm curious if you have this sort of benchmarks.
So I have another benchmark, which is done on Couchbase, I think, which measured exactly this. But it is a couple of machines, so you do have a little bit of communication. But the particular benchmark that we ran was only focusing on reads and gets, so no aggregation. So there's no database connections unless there's a asynchronous replication of the data to the other node, but it's not impacting my benchmark. But I understand what you're saying. That in a real life system, what happens is that network connections tend to be, the problem in throughput. Now, what I want you to remember is that network cards also incur a lot of memory access. So network traffic is also dependent on memory access. So trying to optimize memory access will also help you in optimizing the memory throughput, the actual network throughput. Of course, you will be limited always by the infrastructure that you have. So like you have like 1 gig connection between your 128 machines, 28 gig machines. Yes, of course, you will be limited by the network. But right now I'm just focusing on the network, on the memory part. But I'm gonna get back to the network a little bit later on. Right? A word on hyperthreading. Do you know what hyperthreading is? All right. So for those of you who haven't raised your hands, hyperthreading is a method that was developed by Intel to reuse a core's Intel circuitry to do 2 operations at the same time, because they've identified, same as we did right now, that a lot of most of the time the CPU just waits for the memory to be fetched from somewhere, right? So because of this, it's a lot more efficient to try to do a little bit more processing at the same time. So hence you have what's called hyper-threaded cores. So this is why you get a quad-core CPU from Intel. You stick it into your machine and you see 8 cores in the operating system, because the operating system can see them as real cores. And cloud providers, when they are selling a virtual core, it's actually a hyper-threaded core. Now the problem is that when you're doing a lot of computation, like 100% computation on all the nodes, you're not getting twice the performance, because for every instruction that you're getting into the core, you have to wait for the memory. So you're essentially hitting the same memory bandwidth limitations that you used to. So for the type of workloads that big data applications incur, things where you have a lot of processor usage or memory access, you will not get a performance improvement. A lot of times you will get performance degradation for this. And there's another benchmark that shows this. I don't know if I don't have it here. So you can test it at home. Try to run linpack on a hyper-threaded machine and a non-hyper-threaded machine. You will see that you get about 80% of the performance with hyper-threaded off. So you're not doubling your performance. You're at most at par with hyper-threaded on. But my takeaway here is that a virtual core is half of a real core. It's not a real core. So then don't get confused about that. Now you asked about containers. My perspective on this is that containers help a lot in improving the performance of memory access, because you don't have the same TLB misamplification. that you get from VMs, because you don't have context entries and exits, right? Because they're all processes inside the same kernel. And also you have, it's not yet very easy to do with Docker, but Mesos I think has a possibility to do it, and also you can control it with NumaCTL. You can do NUMA node affinity control, meaning you can pin a container to a CPU, to a NUMA node, and do the allocation properly, not letting the operating system do the memory allocation. So you're not traversing the QPI link. So you're improving memory access times. And by the way, to try to identify the difference in memory allocation, there's a tool called NUMA Top, like Top from Linux. If you use Top, it's NUMA Top. Is developed by Intel, and it shows you how much of the memory occupied by an application is a remote memory or a local memory. So you can see if you can optimize that just by using that. So as I said, I think containers are really helping us getting the same levels of consolidation that you usually get from VMs, or actually more consolidation, because you don't have the overhead of the operating system in every virtual machine, but at the same time not losing a lot of the performance. Of course, you will not be able to run legacy applications in containers, so you can't run Windows on Linux and Windows 95 or something. So for the legacy applications, I'm afraid we're gonna be stuck with VMs. But for new applications, especially things like micro-container oriented technologies, and by the way, I'm not saying anything about databases. I don't know if databases have to be in containers yet, but for the services, the actual microservices, I think containers are absolutely perfect. So I encourage you to try to use them. But there's another disadvantage of using them, and it's the isolation between processes. It's not yet perfect, and there's another study done by some guys from I think somewhere in Latin America, and they studied the effect of running something in another container on another container, right? So, and VMs are a lot better at isolation, of course, because the hardware is simulated. So it's not yet perfect, and there are ways of escaping the jail of a container, because essentially a container is like a ch-rooted environment if you use ch-root. So, but there are ways of escaping that, because it's inside the same kernel. It's not yet perfect. So, from a security perspective, again, it's not yet ready to replace the VMs. So, this is very good when you have a tenancy, the single tenancy of your hardware, of an actual physical box. In terms of performance, this is another benchmark that we did for Cassandra on containers this time, and there is a little bit of performance penalty from containers, but is on the same ballpark. There's another study, actually this is the same study, but they've measured network impact, because it asked me about network. Now, again, what they measured here is essentially latency, right, for different technologies. This vServer is another container technology. It's not virtual, it's not VMware or something like that. So the only virtualized environment is Xen. And as you can see, Xen is about 8 times less fast than a container technology in terms of latency. So again, I'm not referring to throughput, just latency, because latency is impacted by the memory access time. All right. So the problem with running something on bare metal and avoiding virtualization is that, and this is where we come in, is that it's very hard to have the same level of flexibility from a bare metal machine, because you usually have to buy like dedicated servers, and they take months to get delivered, or buy them in your own environment. That's also very complicated. You have to cable it. But there's a new breed of cloud providers out there. They are less known, but they're starting to get a lot of traction, which is bare metal cloud providers, and they offer pretty much the same level of flexibility. You can do it's per second. Actually, you can do start and stop. You can do resume. You can do snapshot, rollback, upgrades, downgrades. You get a lot of the flexibility that you get from AWS, for instance, in them, and we're one of them. We have partnerships with all these technologies. We only do big data because we're, of course, bare metal makes sense for big data technologies, as I said. And when I say big data technologies, I'm referring to the particular type of workloads, not necessarily the fact that it's big, so it's small, but rather that you're using these technologies. This is how it looks like. And when I say you have the same flexibility, for instance, you can click on this and drag it here and create what's called a layer 2 broadcast domain and running your own IP addresses in it. And then you can, to create an instance array, which is a collection of identical servers, you just drag and drop a few things. So, and you get the service in about 2 minutes, 2 minutes and a half. So just the time it takes for the server to boot. So again, you might want to check out this new breed of cloud providers, particularly for running these type of applications. This is the last slide. And again, the things that I want you to remember is that if you're developing something within this, all in-memory field, you might want to look at try to optimize memory access, because that's your primary metric, right? So it used to be trying to optimize disk I/O. Well, now for in-memory technologies, of course, is trying to optimize memory access performance. And there are ways of doing it. You have to check it out. It's not that complicated. It's just a matter of arranging the way your applications are in relation to the data that they have to work on, right? Check out the new bare metal cloud providers. Try to use Docker, at least internally. Try to experiment with it. I really think it's an awesome technology. Disable the THP. The THP, the transparent huge pages, is a way, and huge pages in general are a way of optimizing the TLB cache pressure, because you make the pages a bit bigger. It's like when the new hard drives have a 4K block instead of a 5012 bytes, because if you want to optimize memory access for them. It's the same with the huge pages, a way of reducing pressure, but the application developer has to know that it exists and has to use it properly. And the transparent huge pages mechanism is an automatic system that tries to concatenate multiple 4K pages on a bigger page, which is by default enabled in all operating systems nowadays. But the problem with that is that every now and then you have a kind of a fragmentation issue, and the entire operating system slows down and goes to sleep and then comes back after a while. So try to disable this when you're doing a lot of database-like workloads, because it's not going to help you. It's actually going to make things worse from time to time. So this is actually the primary reason for erratic behavior of database systems. So this is pretty much it. I'm sorry if time was up. I'm sorry.
Thank you very much.
Do we have time for questions?
No.
No, okay. Then we can take them offline. That's fine.
Personally, I was impressed by your implementation with Datamir. 5 times was impression. Implementation Datamir.
Oh,
Hadoop
okay.
as a service.
Oh, yes, Datamir. We're actually very, very good friends with Datamir.
Thank you very much.